Ina mana, ina reo, ina iwi mai na hu a wha, tēnā koutou katoa. Ko pakrag toku inoa, no rira tēnā koutou, tēnā koutou, tēnā koutou katoa. My name is Pat Cragg, and I'm the Acting Deputy Vice-Chancellor Academic here at the University of Otago. It gives me great pleasure to open this inaugural professorial lecture for Professor Boris Baeumer. On behalf of the University, I would like to begin by extending a particularly warm welcome to the members of Boris's family. And they're here with us this evening. His wife Frances, son Albert, studying maths and physics at Otago, and daughters Leilana and Sylvia. And just as importantly, his father and mother are live streaming from Germany, assuming the connections have worked. And we've also got Boris's PhD advisor, Professor Frank Neubrander from Louisiana, and what he calls his PhD grandfather, Professor Nagal from Tübingen, sorry, pronunciation awful. And we believe that there are a number of friends and family members in the USA, Germany and Australia who may or may not be watching. So if you're watching, very welcome to you too. It's really wonderful that all these people can be here physically or by live streaming, because the presence of family and friends is a clear signal of the importance of such an occasion. And I'd also like to acknowledge and welcome staff and students from the host department, the Department of Mathematics and Statistics, and from across the university, as well as members of the wider Dunedin community. And I'd like to give a special welcome to our Chancellor, Dr. Royden Somerville, who attends many of these inaugural professorial. These IPLs are always a time of celebration and pride for the University of Otago. And so I'm delighted to see a really full auditorium, because this means so many people are here to mark this important milestone in Boris's career. To be promoted to professor at the University of Otago is not an automatic journey through the academic ranks. It requires the candidate to show sustained outstanding leadership in at least 2 of teaching, research and service, and then at least sustained outstanding competence in the 3rd. Applications for professorship go through 3 committees: a divisional committee, a staffing advisory committee, and then the Vice-Chancellor's advisory committee. And the opinions are also sought of external and international referees in terms of research. As I hope you're going to learn this evening, Professor Baeumer is a passionate and caring teacher across all levels of teaching, from 100 through to 400 level, and for his postgraduate research students. His mantra, and I'm now quoting from his application for professorship, is mathematics is full of threshold concepts, ideas that you will never forget once you understand them. And he also believes that once a student can explain a concept to a fellow student, they achieve deep understanding. And the phrase I really liked was leading students in this individual journey of discovery is at the heart of his teaching. In recent times, with the support of 2 CALT grants, he has led and is leading a pan-university team to develop a robust tool for assessing competency in numeracy in all of our first-year students, no matter what qualification they are enrolled in. And he's also working on how to support those students with low numeracy ability. He's also a successful, and given the discipline, a well-funded researcher and a leading figure in his field of expertise. His research career has been marked by many successes, which I'm sure you'll learn about during his lecture entitled "The Power of the Limit of a Power." And throughout his career, he's also provided outstanding service to his discipline, his academic department, and within New Zealand more broadly. Last, but certainly not least, Boris is an extremely collegial member of his academic department and the entire academic community. So Boris, on behalf of the University of Otago, it gives me great pleasure to congratulate you on your very well-earned promotion to Professor. I'm very much looking forward to your lecture, and I'm sort of hoping I'll understand it. And I'm now going to call on Professor Richard Barker as the Pro-Vice-Chancellor of Sciences to tell you a lot more about Boris's academic journey to Professor. Nō rea, tēnā koutou, tēnā koutou, tēnā koutou katoa.
Professor Cragg, tēnā koe. Deputy Vice-Chancellors, tēnā korua. Professor Baeumer, tēnā koe. Associate Professor Wakes, tēnā koe. And Chancellor, tēnā koe. Friends and colleagues, tēnā koutou, tēnā koutou, tēnā koutou katoa. It really is a great pleasure tonight to introduce our speaker, Professor Boris Baeumer, to give his inaugural professorial lecture at the University of Otago. As indicated by Professor Cragg, Boris is one of our newer professors at the university, having received a well-deserved promotion to the position of professor in February of this year. Boris was born in the town of Schrumberg in the district of Rottweil in Baden-Württemberg, Germany. I guess that makes Boris a Rottweiler. And I should also say Guten Morgen to Boris's parents in the town of Schrumberg. My father also lives in Germany, so until recently he was only about 30 kilometres from Schrumberg in the town of Schönwald im Schwarzwald. So it's a beautiful region, and this is where Boris grew up. It's in southern Germany, and it's a region known for its beautiful forests and vistas, its wonderful preserved meats, and for its jovial inhabitants, of which Boris is a prime example. And I should say the joviality, not the preserved meat. Boris's interest in mathematics developed at an early age. He was gifted by having a father who was a maths teacher, and I'm sure his father would be very proud to know that this is passed down through the generations, not just to the son, but the grandson, and I'm sure more to come. And Boris discovered that he had a talent for the subject and a deep interest in it. His undergraduate education, or his Vordiplom, was carried out at our Matariki partner institution, the University of Tübingen. And he reports that he was sent from Tübingen to the United States to write his master's thesis because his advisor had noticed that he was spending more time playing cards than on his studies. He thus completed his PhD at Louisiana State University in 1997 before embarking on a series of visiting professorships and postdocs at the University of Nevada in Reno, where he studied the movement of particles through groundwater, an interest that he maintains to this day. He also, at this time, began a lifelong collaboration with Mark Meerschart, who many of you in the Department of Mathematics and Statistics will remember as a former professor of applied mathematics. Boris's research spans some 47 refereed research papers and describes a rich collaboration with people who will be remembered throughout the department. I certainly enjoyed reading through the list. It brought back many memories. Diffusion models feature heavily, as do topics such as fractional derivatives, and I'm sure Boris is going to tell us more about these mysterious subjects shortly. He joined the Department of Mathematics and Statistics in 2001 as a lecturer, and this is an event that I remember well when Boris Francis joined us in that lovely family. And he has since progressed through the academic ranks and reached his present position of professor, which we celebrate tonight. From the very beginning, he established a strong research program, and this included a sequence of Marsdens that began with a fast start in 2004. But it wasn't easy. There's an important tale of persistence here, because this fast start was followed by, I think, 2 near misses, and then Boris was rewarded for his persistence with a full Marsden in 2014, which he backed up again in 2018. So you've got to keep trying. His research has been recognised by his peers. He was the recipient of an Early Career Award for Distinction in Research by the University of Otago in 2005, and he was also an invited speaker at the Royal Society of New Zealand in 2013. As Professor Cragg has told us, promotion at Otago is never just for the excellence in your research. Our professors have to demonstrate all-round excellence, and Boris has certainly developed into an excellent teacher. In his promotion assessment last year, the Divisional Committee, which I chaired, were particularly impressed with the work that he has undertaken, looking at numeracy of students entering universities and ways in which to address what has been a long-standing and perhaps difficult problem. Boris has also developed a strong record in professional service. He served on the Marsden panel, also internally on the University of Otago Research Grant panel. He's also served on the Senate, and in my notes I record that he even spoke at Senate once, which can be a rare event at these meetings. It is now time that we heard from Boris in his own words, and so we'll conclude by noting that mathematicians are notorious for their precise brevity, and Boris is no exception. He summarised the work we're going to hear about tonight in 4 short sentences. And I will summarise this as tonight we're going to hear something about randomness and power laws. Please join me in welcoming Professor Boris Baeumer.
Yeah! Tēnā koutou, tēnā koutou, tēnā koutou katoa. Welcome everyone, thanks for coming. And it certainly is a great pleasure to be standing here, and it still brings big smiles to me, to myself, to me, every time I think about what just happened and how it happened, and I'm certainly happy to be here. And so, tonight I'm going to talk, I guess, about the power of the limit of a power. But before we get into it, the first things I have to do is say thank you to a whole bunch of people. And the first person I need to thank is Frances, my lovely wife. Thank you very, very much. Thank you for coming out with me to New Zealand with no hesitation, building a life here with me. And thank you for suffering through me sitting at the dinner table, rolling my eyes into the back of my head and me wandering off through some Banach space or Hilbert space, and you're having some understanding that, yes, this might be a time where I probably shouldn't be disturbed. So, but also thank you to my parents. Without their emotional and financial support and backing, my journey probably wouldn't have been possible. It would have been a lot harder. To know that you have this backing certainly allows you to take risks with your career, and wherever you go, that would have been a lot harder to do it without. Thanks for my lovely children. You're great. You give me a lot less pain than I thought they would. But also thank you to my former colleagues that started out. I see some of you sitting right there. They started out at the university for hiring me, but also for making me welcome the way that I have. But I guess one person I need to definitely say thank you to a lot is my PhD supervisor, Professor Neubrander, here working with me at the shores of Grand Isle during a sabbatical in 2008. And yes, the story was certainly that I was sent for a 1-year visit to Louisiana, and which then turned into 2 into 5. And we just worked very, very well together. And so thanks to him. Thank you for, where's the camera? Up there. Thanks for all you taught me, and thanks for a wonderful 5-6 years in Louisiana. And some of you might still remember him. The university brought him out as a William Evans Fellow in 2003, I think. But the person who influenced my career the most was Mark Meerschaert, who unfortunately is no longer with us. He passed away last year. But he is certainly the one that took my mathematical career and where I was mathematically as a more pure mathematician into on a more applied course. So walking down the halls of University of Nevada in Reno, at one point he asked me whether I know anything about fractional derivatives, and coming from a transform theory background, I knew it's just multiplying by some ik to the alpha. How hard can it be? So that was my response, and from there, certainly a great friendship and great collaboration ensued, and we meshed really well together. He knew all the applied problems, he knew the modeling, he knew the probability, things that I never want to know anything about, because that was just horrid and horrific, at least what I thought back then. Where I knew then more the PDE theory and the transform theory, and we just really meshed really well. So we'll hear a lot more about Mark tonight, but Mark, this one's for you, wherever you are. All right, but then, a bit like the Oscars, thanks to all my collaborators. This would not happen to you without you. So thanks to Rina, thanks to Dave, thanks to Mishi, Petru, and all the others, who you are. Thank you very much for letting me work with you guys, and keep going there. Then, of course, thanks also to the Marsden Fund for supporting me, and also thanks to the University of Otago, who I guess really nourished me early on, got me reduced teaching load starting out. After my first Marsden, they promoted me early. Professor promoted me early. They even let me have all the overheads from my first Marsden, a nice S account. And that money certainly came in handy then during the sabbatical and so on. I managed to organize conferences from there, and really helped me keep my collaborations and establish collaborations overseas, which is certainly starting out is very, very important. All right, so tonight, as to me, is really a bit trying to answer the big question, which is, what do you do? So there are, I guess, a couple answers. Okay, one would be we predict the future. All right, so that certainly, if you're at a bar or at a party somewhere, that might be an answer that might make me seem a bit more interesting than I really am. If I want to be a bit more honest, then the answer will probably be something more along the lines that we build the tools that allow scientists to predict the future and understand the path. That's certainly how I see the role of mathematicians. And there we go there. So that includes, we create the language to even ask the right questions. And like with any language, there's poetry, there's art, there's beauty in the language. There are ways where we can actually phrase problems or solve problems that are just absolutely elegant and fantastic and nice to see. And there are plenty of mathematicians who focus on that and could care less about the rest of the applications. However, another answer to the big question would be, I've worked with models. That would probably also be a good answer to what do you do? So models, well, we build them, build conceptual models of reality and then use mathematics to explore what the model does and then infer, hopefully, back to reality. We develop proof solutions, we improve on the solution approximation techniques. To me, that mostly encompasses most of what math is about. Okay, so what is a model? Obviously, could also be one of those. Okay, or it could be something along those lines. But now the real question is, what do those three have in common? there's something very fundamental in common, namely, they are all really just depictions of reality. Okay. So even though the first one walks and looks alive, she is not real, but she lets me see how I would look like if I put on that dress. At least some models are probably better than others in, describing what you want them to describe, but, the toy thing, I can pick it up and see how things move and what the wheels do. I probably don't get the awe of standing in front of a real-sized engine, but I can understand a little bit what's going on there. And similar on the right-hand side, that's on purpose so small that you can't really read it, but it's an aquifer and equitards and their relationship, and I can now build numerical simulations of things like this and see kind of how it would respond to certain different pressures and rainfalls or so on. And depending on the question asked, I can have a more accurate or less accurate answer. All right, so overview of tonight's talk. So first I'm going to talk about the limit. Then I'm going to talk about the power of the limit. Once we're there, then I'm going to talk about the power and the limit of the power. And the title, The Power of the Limit of the Tower. And if time permits at the end, I'm going to talk about the limit of the power of the limit of the power. And then according to the program, we're going to have some light refreshments at the staff club. And after that, I hope we can all join me for some heavier refreshments at Eureka's after that. All right, so the limit. So the limit. What is the limit? It allows you to talk about approximations without having to talk about the algorithms or specific approximating procedures every time. Okay. The square root of 2 is a limit of a procedure that would allow me to estimate the square root of 2. I take a number, I square it. If I'm less than 2, I make it a little bit bigger. If I'm bigger than 2, I make it a little bit smaller until I get to the square root of 2. But I'm not going to talk about this every time I'm going to talk about the square root of 2. I can just talk about the limit. Okay. The same, if the limit is some sort of function, some sort of curve, some whatever type of object. So a limit is an emerging picture or object, such as a number. They often have special properties that the things that approximate the limits don't have. Okay. So, got my LSU dice. I'm going to talk about limits of random variables, so let's roll some dice. Okay. So if I take a dice and roll it, we know we're going to have a probability of more or less 1/6 for each number. Okay. If I roll 2 of them, there you go, 2 ones, that probability is rather small. That's only has to have 1 and a 1, so it would be 1/6 times 1/6 gives you 1 in 36. To hit a 3, you can get a 1 or a 2, or a 2 and a 1. It's twice as many. Hit a 4, a 1 or 3, a 3 or 1, or a 2 and a 2, 3. And so that goes up like a ladder and then it comes down like that. What about if you have 3 dice? Well, looks like that. What about 4 dice? 5, 10, 20, 50, and then the whole thing kind of disappears. Okay. So we don't really see too much disappears. So that's a little bit silly. 500. How about we do this over again and don't leave the top at 1, but actually just show what's going on. Okay, so let's do the same thing over again. All right, so just the scale here on the left as such that we keep the peak up. Okay. So 10, 50, 100, 500, 1,000. And what you see is that we're going to get narrower and narrower, that we're going to have a little needle right there where the mean 3.5 is going to be, and we discovered the law of large numbers, what it's called. Okay. So, well, we might want to zoom in into that needle a little bit more to see what's happening there. Oh, it's 5,000. Okay, so let's do the same thing again, but now I'm not going to show every possible output. I'm only going to show the bit that is within, the probability is within 10 to the minus 9, okay, of the maximum probability. And so if you do that, what's happening there is, okay, that at some point the numbers down here just change, but the picture itself doesn't anymore. And this is what's called the central limit theorem. So this below, the limit of, whoops. And so if we now change the scale to a logarithmic scale, so I don't have for 1, but I now have 10 to the minus 2, 10 to the minus 4, 10 to the minus 10 to the minus 8, what we're going to see is a nice parabola right here. Okay, so now I'm going to take my beautiful die, and change it a little bit. So I make a 5 here and a 5 here. So now I'm going to have 3 5s and roll it again. Okay, so now my probabilities have changed. Okay, how did they change? Well, that way. I don't have a 3 anymore. I don't have a 4 anymore. Okay, but I have 3 5s and so on. If I do this to the other die as well, what's going to happen? How does that look like? It looks like that. Okay. I don't ever get any 5s together. I'm not going to get any 9s, because the only way I could get a 5 is by a 1 and a 4. The 4 doesn't exist anymore, or 2 and a 3, and the 3 doesn't exist anymore. And I get a distribution that has like 3 bumps. Okay, if I have 3 of those dice, okay, I'm going to get 4 bumps. Okay. 4 dice. 6, 7. All right. And what happens is the central limit theorem again kicks in, and you're going to end up with the same distribution as you had before. The peak a bit more, well, it still will be central, but of course the number that sits underneath the peak is still going to be on the mean, and that's now 4 times the number of dice rather than 3.5 times the number, because the average is now going to be 4. And it's still going to be a nice parabola. Okay. So that's the limit. The power of this limit is, well, we have our whole discipline named after it, basically. It's statistics, really is based on that. It's a better statistics, it's almost universal. The limit described by 2 parameters, but it really, the most important thing is that it has a scaling property. That x plus x is not 2x, but x plus x is square root of 2 times x. Careful, don't use that in your math at high school. But 1 plus 1 is not necessarily 2. Okay. But what it does is also it links time and space. Okay, so if you think that you can roll a dice every minute, then on the left-hand side, it will take you 2 minutes or 1,000 minutes if you have 1,000 dice. Where on the right-hand side, you just take your original distribution and you can blow it up. And so you're just making it larger, and you're getting a much, get a spatial feature that you didn't have in your temporal. So it links time and space. So this limit distribution has much, much stronger properties than the distributions that approximate it, that come together and give you this limit. Okay. And so this then also allows you, to do things like stochastic integration. It's basically the basis of all kinds of diffusion models, diffusion and uncertainty component of more complex systems, and so on, and the list goes on and on and on. This is the model that most of our work is actually based on. Okay. So, the power. I want to talk about the power. And one prime example that things are slightly different when you talk about power is money. Okay. So let's do a little thought experiment. Okay. So let's assume we take two people in this room at random, and their combined height is 4 meters. Okay. What is the individual height? Oh, I thought Jörg would be here, but close to 2 meters each. Okay. What about if their combined income is $600,000? Would you assume that each of them is making $300,000? Or would you say it's much more likely that one of them makes $500,000 and the other one makes $100,000? I mean, how many people do you know that make $400,000 a year? Not too many. I mean, you know, one just moved to Australia, I guess, but. But actually, that is an interesting thought too. How many people do you know that make twice as much money as you do? And of those, how many do they know that make twice as much money as them? And among those, do you think they know somebody who makes twice as much money as them? And so on, and so on. Does anybody know that having enough money, a lot of money, doesn't make you happy? Because there's always somebody else who is a lot richer than you are, and you get new circles, and again, there's going to be somebody who's a lot richer than you are. Keeping up with the Joneses isn't getting you anywhere. Okay, and this is not just folklore. This is actually pretty. Pareto discovered this in, I think, 1905. But here's a more recent publication here that Japanese personal income, French total assets, and they follow this straight line in log-log plot, which means it is a power law relationship between the two, and hence also the work of power to those distributions. Now, we also see that in self-organizing things, like YouTube hits. I mean, you can get a much straighter line than that. Or city sizes. Or dispersal. Okay, seed dispersal. So what I did say, they took, I forgot which tree, they took a tree and put up traps, and then said, okay, let's see where we can find the seeds. Okay, and so the classical model, based on our central limit theorem, I would say that should look something like that, or maybe like that. But they found them basically everywhere where they put up traps, which can be very frustrating. And say, okay, I guess we have to do that again and put them even further out. Okay. It's also in the dirt. Okay. So we have a nice correlation of the area and the frequency, how often those landslides happen. So big ones happen not as often as smaller ones, but they actually follow a fantastic power law. But you have to wonder whether it's actually just something of the universe. So what you see here is over 12 orders of magnitude. That's big. Okay. The range of sizes of particles hitting our planet. I mean, can't get much straighter than that. Okay. So it seems to be, well, why? Nobody knows why, as far as I know. Okay. But it would be quite interesting to know, I think, why those power laws are there and why they persist. So what I can tell you later on is that once you have them, Why you can't get rid of them. Okay. But how you get them in the first place, I think, is still a big mystery. Okay. We can also have those power laws in time, called intermittency, or a hidden Markov process sitting behind something, continuous time random walk, all kinds of names for it that are based on that. So these are now tiny quantum dots. They blink. Okay, and so they just looked at how often do they blink, or what is the time between the blinking, and the time between the blinking is again sits on a straight line in log-log plot. So if something happens every time you have a blinking going on, then you have a process again where you might want to have some understanding of those powers. Okay, last one about the Earth. I like those slides. So whenever you need a reference to do a scale, okay, you're probably, you're in a more or less scale-free regime, and you're going to probably have to find some sort of power law. Okay, so here we have a third. There's a little, I hope it's visible, a little lens cap right there. Okay, here's another one. The lens cap is over here, and they look reasonably similar. Okay, but we have it for scale. But the real revealing picture is the following. Here's Scott Tyler next to his huge lens cap. Okay, trying to make a point that scale is really, really important. All right, so the limit of a power. So what happens if we, instead of starting with a dice, if we start out with something that has a power law like that? Okay. So, the easiest power law, we say that the probability of my random variable exceeding a number decays like into the minus 1.5. That's where the power comes from. This would be a nice straight line with slope minus 1.5. Okay, so in the beginning, the probability would look like that. Then it comes down. Okay, and seems to stabilize. Okay. So in this case, it actually does not converge towards the Gaussian. It will converge towards something that looks like that in semi-log plot. It's not this parabola. It's something that still has this power law on the right-hand side. So it's like, it is a limit. It is the limit, and it's called the stable limit, or a stable density, in this case, that those power laws will converge to. So the limit of power laws is actually not the Gaussian, and the Gaussian is more or less universal, except in this case. And so the power of the limit of the power is now where my research is. And this is about now exploiting those limit functions, those densities, to see whether we can do something similar as we did with the Gaussian. Can we describe an evolution of particles, of whatever it is, of seeds that have those dispersal probabilities, that have those intermittencies, or whatever it is, and exploit the scaling property of those limits. So that because we do have this scaling property. So again, we have this linkage between time and space. Now it's not 2 to the 1 over 2 to the 1/2, which would be the square root of 2. Now it's 2 to the 1 over alpha, where this alpha is the parameter, that decay parameter of my original density. Okay, so I gain one more parameter. So instead of 2 parameters, mean and variance, now I have 3 parameters, which kind of is the location and the shape, and then the scaling, the tail. So this is the basis then of my fractional diffusion models can also be used to model intermittency. Okay. The governing equations, they do have fractional derivatives instead of second-order derivatives, so the Laplace operator will turn into some mixture of fractional operators, whoever knows. But one of the problems is that there's no nice formulas for the density of the limit. So the Gaussian has this additional nice thing that is just e to the minus x squared times some constant. Okay. This one here, we only know as a nice formula in transform space, whatever that is. But in real space, we can make a special function, and now computers can handle those rather easily. But it also, to me, also explains a bit why they haven't been used a lot more for much longer. All right, so where does this take me? So first, back in 2001, still in Reno, the first I worked with Mark was to say, okay, we can extend this basic limit theorem, which was already discovered by Levy in the 1930s, and to more than one dimension. Okay, so this is an article about operator Levy motion, so those are Levy densities, and how to extend this in 2 dimensions, and get estimates from there. And then apply those, not just in physics, but then also in hydrology, so that is in water resources research, okay, to get their solutions, and hopefully then can estimate parameters from a given data set of some plume that sits underground and want to describe of how this might evolve over time in the aquifer. Okay. So operator scaling, solute mixing, and dispersion. And so you work your way up then through the years. Okay. Now, exploiting the fact that we have this relationship with space and time allows you to move away from a strict spatial component and say we use the temporal road first, and then follow the flow lines to adapt to a special geometry. Whatever flow fields we have. In order to do that, though, we first had to actually prove mathematically that we are allowed to do that and that we can do that. So this is a paper, Journal of Evolution Equations, together with Michi and Marcus, that is unreadable. So I thought we had a reasonably nice engineering approach to whatever goes on. Then the referee got their hands on it and made it more modern and mathematically, and it turned out to be completely unreadable. But it's still nice and true. But it took us a few more years to translate then whatever we did to be able to say, okay, you can take your big groundwater dispersion model and then use this fractional bit to say on the subgrids, we can accelerate in each subgrid our particles the way they need to be accelerated to give you those possibly fast and long jumps. All right. Now, once you have your basic diffusion model going, you can extend on those by now adding things like reaction. Reaction means, quite often in the biological world, birth and death. Okay, you die, or you regenerate and multiply. And so here we have a fractional movement, so a movement where we have a power law dispersal, and then we have some growth and some decay wherever we are, and manage to describe this reasonably well. The one thing that we cannot really describe, and I'll get to that a little bit later, is that all those models will be mean field models. Meaning the only thing that we can get out of it is what will happen on average, so we will not be able to describe the dandelion, we blow it, where's the seed going to go and where's the next colony going to be established, but we can potentially get a risk surface of what the probability is that we're going to see something 20 kilometers down the road, 50 kilometers down the road. Where do you need to put on your eradication effort? How far do you have to go to be 95% sure that you got most of it? And then, we also provide numerical tools to actually be able to say something about that. I guess the one anecdote that I was trying to get rid of at some point, that's still on my tongue, is one of my favorite ones of Mark, is where I was really, really excited to figure out something, and he basically said, it's nice that they understand something, Boris. Okay, it's not worth a thing until you explain it to somebody else and they understand it, because otherwise only you know it, and what's the use of that? Okay, and that not only, for him, not only meant that he should be able to understand what I'm thinking, but then also the scientists should be able to understand what we are thinking, and that might then involve not just putting it to somewhere into a science journal, but you might have to explain it to the biologists, to the ecologists, to the hydrologists, to the physicists in their own language, so it can actually be used. And I think that was very sage advice. Okay. So here is another early paper talking about intermittency. So that's the first time where we basically inverted the spatial process into a time process, and showed that if you have a nice process that doesn't have intermittency, if you throw intermittency on top of it, so things only happen when your quantum dot is blinking or whatever it is, that then you're going to have a nice solution that you can get from the old solution by just randomizing time. Okay. I wrote up the main proof of that one afternoon in a little Word document that big, and said, look what, that seems to be that. I don't know whether it's worth anything, and I didn't really think it was worth much. And Mark said, oh no, that's kind of neat. Let's write this up and send it in. Like, okay, but I have a feeling that's been done somewhere else. I can't quite see it. But no. He insisted that we send it in and put in. So we put it in this little rinky-dink journal that's just started up on fractional calculus. It is one of my most cited papers. But I don't get any credit for it because it was in a journal before that journal was really indexed within any of those citation metrics things. So if you look at my H value, it's one more because of that one. Okay, and that then ballooned into, again, showing how this would apply or how this would affect solute transport in groundwater. So now we have an immobile zone, basically where the particles sit while they are intermittent, while they're not blinking. Okay, and how they move when they're in a mobile zone. And there's a nice decomposition and nice math behind that. Okay, then we can link time and space as well. And this one here would be something where we have a finite mean waiting time, but infinite variance waiting time. And then a few papers coming after that. Okay. A big part of the research is also what to do with numerical approximations. And so here's one way to approximate our solutions, doing it better than most of them did. We have higher order conversions. And there was a well-received paper. And then my most recent Marsden is now what do you do if you have those scaling limits, which are things that are, by their very nature, are supported on all of space. Even the normal distribution e to the minus x squared is positive, from minus infinity to infinity. What do you do? How do you restrict this to a bounded domain? And so we are exploring that in our current Marsden. All right, and this was more the write-up for the George. So the last 5 minutes or the last 3 minutes, I'll talk a little bit about the limit of the power of the limit of the power. So, told you all kinds of things and showed you all kinds of fancy journal titles. Okay, but it's not a panacea. So, one problem is, well, it's only 3 parameters. It's still very parsimonious models, but they are still very hard to estimate by their very nature. Okay, they are low probability of making very, very large jumps. So if you find 1 or 2, and, well, they flew 10 kilometers further than what they had before, your tail estimate or whatever you have will vary greatly with that. So unless we find a way to be able to predict our tail parameters from other mechanisms, okay, why is this self-organizing thing happening? Okay, why is this giving us those power laws? Why are there chunks of stuff flying through space that are a power law? Why is YouTube working the way it is? Not many people know about it. They certainly haven't told me about it, and I haven't found about it. There's a book by French mathematician Sabatier, I think he's in Bordeaux. He lists about 14 different methods that will generate power laws coming out, but how each one of them would really apply to a given situation is, again, still a total mystery. I already talked about models are kind of mean field. We can only give a risk surface. We cannot really predict where the next colony is going to be. What we can show by a simulation is that if you were to build a model where you take seeds and you throw them randomly out and then build new colonies, that the only way that you can get patterns that you might see in nature, that you have a main colony, another little colony, different little colonies rather than one big blob moving out, is that you're going to need power laws in order to get you out there. Okay. And then, even though I had a Marsden on that, the quantification of uncertainty is still a mystery. We made some progress, but to really know how far, what those error bars should be is very hard. All right, and with that, thank you very much.
Tenakoto kata. It is my great pleasure to be here at Professor Baeumer Boris's IPL and giving the thanks as head of department of the Maths and Stats department. I'd like to thank Boris for the really interesting and informative lecture on the power of the limit of a power. Have to get that right. As well as your heartfelt tribute to your longtime collaborator, Mark Meerstat. That was lovely. So you've taken us on a journey of discovery to the limit of a power. Through the exploration of that limit distribution, you've shown us the very useful properties it has and how these can be exploited to give valuable insights into what happens in the limit. You've then connected this fundamental understanding of the limit of a power to the use of power laws in such diverse disciplines such as ecology, physics, statistics, mathematics, finance, possibly gambling. I actually think that the answer to life, the universe, and everything is not 42. I think it's a power law, and I think Boris has discovered it. I would also like to acknowledge the important work Boris has done supporting students with low numeracy as well. The peer-assisted numeracy PAN programme he was instrumental in developing has the key message he told me yesterday: confidence comes from competence. Boris has connected us to this idea tonight, I think. He's demonstrated that by having confidence in the limit of a power, we can be empowered to build expert models which will ultimately help us understand the world better. So thank you for that, Boris. That was really informative. I've also discovered a few things about Boris. I think he's a secret ABBA fan. I noticed the money, money, money quote at the top. So that's an interesting thing I'll take away with me. So I would, Boris, please, we have an item of appreciation here. Your lecture today, so please accept this on behalf of the university. I'd just like to thank again everybody for attending this really special occasion for Boris. In particular, Boris's family, both here and in Germany, Australia, and everywhere. His friends, his colleagues, and all the students that have turned up as well. So thank you very much. And I'd like to invite you to join the academic party for refreshments in the staff club now. Thank you.